My name is Hussein. Welcome to WestGrid seminar, and good morning to West Coast and good afternoon for the rest of Canada. And thank you for those who are joining here locally in our Access Grid room. So I'll be going to present an introduction to OpenMP, and this is going to be an introductory seminar. And we will, as Aaron mentioned, we will have some examples that you will go through this if you have some SSH session open. I'll give you a brief introduction before diving into the OpenMP itself. And I'll start with the high-performance computing. But what is it and why do we need it? In a very general term and not very maybe precise description of high-performance computing, HPC is a way to take advantage of aggregate power of more than one computer. So if you have let's say 10, 100, or 1,000 computers, and you want to take advantage of this aggregate power, that's we call it HPC. As I said, this is not very precise description, but this is a general idea. That's why do I mean with HPC when I'm referring in my slides. And when you have a HPC or high performance computing, you can have the ability to run multiple programs at the same time. So you can run the same program, let's say, with different input files, 100 at a time. For example, if you have 100 compute nodes in your disposal, or you can have even go further, and then you can split or divide your program in a way that you can run part of your program concurrently on different machines. So the first question that you may ask is that why do I need HPC? HPC is just maybe it's not for me, but as the matter of fact is that single computer has its own limitations. So you cannot have more than, let's say, a few cores or just limited amount of memory in one box of a computer that you have. So that's why when your program grows or you need more power, so you need to have more and more compute nodes. The other thing that started a few years back, that traditionally when you had an issue with your performance of your program, you could wait 1 year, and then the next year CPUs will come with a higher CPU frequency, and then you can run your program faster. But that's not the case nowadays, that each year we see more cores instead of getting more powerful CPU power. You can have more cores per CPU. So you cannot just run your program simply by waiting for a year to get it better or newer CPU, because it's going to run on the same, almost the same, or maybe even weaker core. And then you have to use, but this opens up some opportunity to run or modify your legacy codes to run on more than one core. So you can gain or get benefit of having multiple cores. And of course, I know that scientists, they have lots of problems, new problems. So you can, let's say, add a little bit more accuracy, and then you need maybe 10 times more compute power. So there's no limit for how many compute nodes or compute power you can have. And nowadays, this big data, it's lots of data to be processed as well. So these are something that you may consider why you need HPC. So when you have more than one computer, so you have to decide how to put these computers together. The first approach could be this corner here. It's a shared memory approach, that you have a memory and then a few CPUs or cores that they are using the same memory. Nowadays, most of the computers, even your laptop, they come with 2 cores or 4 cores, or maybe even more or less. It depends on the configuration. So basically, you have more than one CPU or computing unit in your laptop or in your desktop, which they all access to the same memory, or the RAM, or physical memory. By memory, I mean physical memory or RAM, not hard drive. The other approach is if you have more than one compute node, not just one box. If you buy 10 desktops, for example, now you want to get you want to use the aggregate power of these 10 desktops, then you have to somehow connect these desktops or computers together to get the illusion of larger machine or larger computer. Then you need something like a network that they connect these nodes together, and each one has its own memory and set of CPUs. So in this picture, it shows one CPU, but each node can have multiple CPUs. Imagine that your desktops, they have, let's say, 6 cores each, And then if you connect these desktops using a network, you will have each node with 6 cores and memory and so on, and then it will be distributed memory, we will call it. So OpenMP, that we will be using on shared memory machines, not distributed memory. That's for distributed memory, as you will see in this slide, we are using another library. So corresponding to each architecture, we use different programming models. For shared memory architecture, we use multi-threading, which we create multiple threads within a program, and all the threads will use the same memory space. So they will access to the same memory, but they will be running on different compute units that you have on your machine. So basically, you can run your multi-threaded application on your laptop, which has more than 1 core. So you can gain some benefits over there. The good thing about multi-threading is that it's easier relative to the next option, which is multiprocessing. It's easier to program, but it's not very scalable because you are limited to the number of compute units that you have in one box. So you cannot use, even if you have 10 desktop or 10 compute nodes in your disposal, with multi-threading, you are just limited to the number of cores that you have in one box, and the same thing for memory. And there are different ways to do multi-threading. If you are using, let's say, Java, Java has its own thread library. If you are using Python, it has its own packages. Even if you are using packages like R for skill analysis, it provides some sort of packages which, at the end, it's underlying it. They are using the same concept, but it does a different APIs and different high-level interface that you may want to learn how to use that. But ideas, you can see that if you learn some ideas here in the OpenMP, it will be easily applicable to other programming languages, as I said, even, let's say, like packages like R as well. The other thing which corresponds to distributed memory architecture, it's called the multiprocessing. So in this case, you have multiple programs or multiple processes running on different, on many computers, and they communicate through network. So you need a different library, which is mostly it's based on MPI or message passing interface. So, and it's harder to program, so you have to take care of who is talking to who, and then which part of data it's going to be shared among the different processes, but it is scalable. So in WestGrid, I'll give you a brief introduction to WestGrid machines. But in WestGrid machine, most of the computers are distributed architecture, so if you have an MPI program, you can easily run on WestGrid systems. So here's the same slide that I just talked about. So this is a mini introduction to WestGrid. So if you want to use WestGrid, you need to have an account and SSH client. So you will be using SSH client to connect to one of these WestGrid machines. And in this presentation, we will be using Grex, which is a computing facility hosted at University of Manitoba. If you have any questions, you can send those questions to support@westgrid.ca, and then there are so many people with different expertise that they will help you with your different questions regarding your programming and running your application on WestGrid. And if you go to the westgrid.ca, you will see lots of resources like information about from quick start guides to different machines up to the previous presentations and installed software and so many things that you can find on westgrid.ca website. As I promised, at the WestGrid, most of the machines are distributed memory architecture, including Grex, that you have, let's say, 316 nodes. Each node has 12 cores, so totally it's about maybe 3,700 cores, but not in one box. They are, as I said, distributed among 316 nodes. So you have to use MPI to take the full advantage of this system. However, each compute node in Grex or other systems in WestGrid, they have more than one core. So in Grex example, we have 12 cores per node. So you can have 12 threads running on one machine. So basically, you can run your own multi-threaded application, even though it doesn't scale well because it's just we are limited to 12 threads. But there is one big machine in the WestGrid. It's called the Hangabee, and it's at the University of Alberta. So if you need multi-threading for a huge number of threads. It's got 2048 cores, which if you run a program, multi-threading program, virtually you can access to 2000 threads. And it's got 16 terabytes of memory, so if you have a program which requires lots of data processing and memory, that's the machine that you should use it. But it has a separate account, so you have to send a request to accounts.westgrid.ca to get the account for that. But I'm not going to in details of that. But everything is on westgrid.ca. You can get the quick start guide to Hungary. Okay, so it's time to do some logistics before diving into the OpenMP. So make sure that if you are attending this webinar, you have a SSH client. If you are using Mac or Linux, you can use this SSH-Y if you want this X tunneling and username at grex.westgrid.ca. And if you are using Windows, you can use SSH client of your choice, anything that you have already installed on Windows. It doesn't come with SSH clients, so you have to install your own version. And once you logged in and everything seems to be fine, so you are on Grex, next you have to find the samples or examples that I will go through in this webinar. And then you can, I copied to this folder to those who have RSVP'd. So if you log in and you are one of those people who have RSVP'd before, you will see this folder under your home directory. But just in case if you don't see it, you can use the cp-r/global/scratch/workshop/openmp-wg-2015. And don't forget this dot, which means that copy from that folder from that location to current location, which is, I assume, it's your home directory. Now that you have this folder in your home directory, what you want to do, you want to get access to one of the compute nodes that we have allocated for this webinar. Everybody that, if you run this command, sh space omp_node.sh, what you will get 4 cores in one of the machines. So you will be transferred to one of the machines, to one of the compute nodes, and you will have 4 cores available that we will run our programs with, and then you will see how we can use different multi-threading approaches for that. Okay, so it's better because it will take about maybe half a minute or a minute or two to get those cores. So if you are in the folder, try to run this command sh space omp_node.sh, so you can get by the time that we get the first example, you have access to that compute node. And one thing that I already have some files which you can see that they have this dash template in their file name, which those are the templates that you can modify while we are talking about the different directives of OpenMP. So you can modify those, and you can see if you can really apply those that we are talking on the slides in your program. And then to edit those files, please use one of the editors in Linux. I don't know, it's Vim or Nano, Pico, or whatever. That it's mostly text-based. It's preferred. And don't try to copy it to Windows, edit it, and then copy it back, because you will get some extra characters or something undesirable that maybe it will prevent from compiling the code. Okay, so I think that's enough for introduction. Let's get started with OpenMP. So OpenMP, or Open Multiprocessing, is a library, and it's a de facto industry standard for running multi-threading applications. So what it does, it gives you ability to divide your work. And your work, I mean that your program. You can write your codes. You can split different parts of your program. We will see all these examples how you can make a for loop or do loop, and depending on which programming language you are using, to start multiple threads, and each thread will run part of the program, and then hopefully you will get some speed up by running multi-threaded applications. So OpenMP consists of 3 parts. One is a compiler directives. That's what you will need to tell compiler that my code is not a simple C or Fortran code, it's a multi-threaded code. So that's a compiler directive that we will talk about. There's a runtime library that it gives you some functions that you can use in your code. And there are some environment variables that, again, we will use it in this webinar. So depending on what you want to do, you can set or change few environment variables. The good thing about OpenMP is that it's supported by most of the compilers, major compilers like Intel or GCC. If you are using GCC on Grex, you can compile your programs, and I'll be using GCC to compile these examples. And you can use with C, C++, and Fortran programs. I'm not a Fortran expert by any stretch, so my code, and I will have some examples in Fortran, and I have all the examples that you have already copied or you already had in your folder. It's both in C and Fortran, so those are the extension is F90. It's the same code in the Fortran, but some of the codes I will be describing in a slide is just only C code, but you can have exactly the same thing in Fortran as well. So the first thing is in OpenMP, as I said, you have to somehow tell the compiler that your code is not a regular serial code. So you have to tell compiler which part of your program needs to be multi-threaded, and that's how it works with in C and C++. We will start with # pragma space OMP. So that's the directive that you start telling the compiler that now I'm starting those multi-threaded areas of my code. And if you have a compiler that doesn't understand OpenMP, or if you don't give the proper options to the compiler to compile with OpenMP, these lines will be ignored. So that's the beauty of OpenMP, that you can have the same code that you have the serial version. You can compile it with OpenMP parameters or without parameters. We will see that there are some details that you have to be careful about, but generally speaking, compiling is easy. Sometimes you may get some warnings if compiler doesn't understand this directives, but that should be mostly okay. So in C, as I said, it starts with # pragma. And if you have a block, it follows the same blocking rules of the C programming language. It starts with a curly brace and it ends in the curly brace. In Fortran, however, all the directives start with this exclamation mark, $OMP. And it doesn't matter, it's a lowercase or uppercase. And then you will have each of these directives normally finishes with the end part, which we don't need it in C. So for example, if you want to make it a section parallel, you write in C, you say pragma OMP parallel. So this part of code will be the parallel region. But in Fortran, you have to finish it with OMP end parallel, saying that's okay, I'm done with the parallel section. Now I will go with the serial code. The other thing, as I said, so you have to give the compiler some directives or some flags to saying that, okay, the code that I'm going to compile has some OpenMP directives, so be careful about that. And that's how we compile our codes. And you give this -f OpenMP flag to your Fortran or C or C++ compilers. So this is normally, it's for GCC compiler. But fortunately, Intel compiler accepts the same flag. So if you are using Intel compiler, you can still use -FNOP, although the preferred flag for Intel was -OpenMP, not without Fs. But as I said, -F OpenMP should be fine for Intel as well. So I remember in a couple of slides back, we said that I told you that OpenMP has 3 components. One is the compiler directive, that you saw one of them. It's OMP parallel, that's the one. The second piece was a library that we will be using in the code. And the third piece was the environment variable. The first environment variable that we will be using most of the time, it's called OMP_num_threads. This is all capital. And this is the environment variable, which tells the OpenMP program that's how many threads you are going to use it. So if you don't specify how many threads you want, And then if you happen to have, let's say, for some reason, 12 threads, hardware threads, or 12 cores on your machine, it will consume all 12 cores or 12 hardware threads. This is how you will limit the number of threads that you want to use in your code. And in our examples, we will be using up to 4 because that's how many cores, actual physical cores, that we are going to get from the Grex here. And it depends on if you are using bash, that I will be using most of the time. You will use this export space, this variable, OMP underscore num underscore thread equals to value. And value, as I said, most of the time will be 4. But for test purpose, we will start, let's say, with 2 or 3 or 4. And we will see if we are getting any speed up by increasing number of threads that we are using in our program. And if you are using a TC shell, so you can use the setenv command, OMP underscore num thread. So the name of the variable is the same, and the value should be the same, let's say 4 or 2 or whatever that you want to say. And in the example, as I said, most of the times we'll be using 4. Okay, so I hope that you already ran that sh underscore OMP node. So you are in one of these compute nodes, which you have 4 cores in your disposal. And please check if you are not in the OpenMP-WG-2015 folder. That's most of the, or all of the codes will reside. It's just please just use the cd command to change the directory to that folder on the compute node. So don't exit, please don't exit from the compute node. So we have something to do on those compute nodes. And then once you are here on compute nodes on the same folder, hopefully you will be able to follow the commands that you will see in the following slides. So you can compile your code, you can run your code, and hopefully you see the results that I'm seeing on my terminal. So sometimes I can share my terminal so you can see exactly what I'm doing, but so far everything is on the slides. So the first example that for most of the programming language, we start with hello world, and in this case we call it OMP underscore hello world. This is the basic program that shows how to use OpenMP directives and how to compile it and what the output will look like. So the first slide is on slide 12. It's a C code, and you can see the on slide 13, it's the Fortran code. It should produce almost the same output, and it follows the same rules, or it shows the same concepts. So it's located at OMP underscore hello world.c or OMP underscore hello world.f90 in the folder that you just copied, or you are in the same folder. So I'll share my terminal just briefly. So you can see that I'm in the folder OpenMP-WG-2015, and if you say ls, you will see that there are so many files. That, as I said, each one is a .c or .f90, and those have a template in the name. You will have a chance to modify that to use it. So the first one is called OMP hello world.c, so you can see as I highlighted here. And that's the code that we are going to run it and see how it looks like when you're running on multiple threads. So, as I said, this is the Fortran code. And then here how we will compile it. Oh, sorry. I have to come back. OK, I'll see. So to compile it, let me switch back to my slides. Okay, so and if you have a local copy of the PDF of the slides, you can open it in your own local window, and then when I'm switching to terminal, you still have the slides on the screen. You can follow it, but I switched it back to a slide. Hopefully you see it. The compiling, I have GCC version here. If you want to compile with GCC, we are using -f OpenMP then space, this is the name of the first program, Hello World program, which has OpenMP directives, and -o for those who haven't used GCC or a compiler before. This means that after compiling the code, name the code as OMP_Hello World. So our program is helloworld.c, and our executable has OMP_Hello World name. So there's no .c or .anything. It's just this piece is the executable code that we are going to run. So if you prefer Intel compiler, you can use ICC. The same, as I said, fortunately, it accepts the same argument or flag for compiling, the same code and the same output. And if you are using the Fortran code, you use gfortran to compile your code, and it will be the same executable. So you can name the same executable. So that will be all OMP_Hello World. So this is the first piece that we compiled it. So we had the OpenMP directive. Now we compiled it. We have executable. And then to make sure that we are only using the 4 threads, not more, we are using this OMP num thread environment variable. So you have to run it if you haven't run it yet. So just type in, if you are using bash, export space OMP num thread equals to 4. And then this should give you, or the program will use 4 threads when it's running on your machine. Then we will run this code with ./OMP_Hello World. What's that? Oh, okay, yeah, 4 threads, it's but yeah, for this presentation or webinar, the way that we set up the compute nodes, maybe you cannot use more than 4 cores, but this is a good practice to make sure that you know how many threads you want and you specify before running your code. Otherwise, as I said, it will maybe, if you see 12 cores, it will use it 12 cores and so on. So I will switch back to my terminal to make sure that you follow what I said on the slide. So I will do gcc-f OpenMP, my OMP hello world.c-o OMP hello world. So this is a command that I have to use. Then I will export OMP num thread equals to 4. And then I will run OMP hello world. And you can see that I've got this 4 threads here, and threads are numbered from 0 up to n-1. So we requested 4 threads, so we will have thread 0, 1, 2, 3. So you can see that's hello from thread 0, 1, 3, 2. And the order, you can't guarantee the order of threads, because depending on when you are running this code and what the situation is, they can run in any order. So I'll give you a minute to see if you can compile it, run it, see if you can get the same output that you see on the slide and on my terminal. And if you do, I'll keep on going on the slides. Okay?
Oh, that's probably has it.
Okay, that's good. Yeah, there is open num thread, so you have to have S at the end. It's not just thread. That's good. We have engaged participant. That's good. So I will switch back to my slides, and then we can hopefully get going. Okay, so that's the first one. As I said, it can be C code or Fortran code. It doesn't matter. You should see this 4. And if you change the num threads to 1, 2, 3, 4, whatever, you have to see corresponding number of threads. So if you make it 2, you should only see thread number 0 and 1 and so on. So in my case, this was just one run that I had it. So you can see that thread number 1 is the second last one. But depending on run, you can see different values. I haven't specified. Let's see. That's a good point. It's the same effect as not having any OMP num threads. So don't specify 0. In this case, again, it's okay because you are limited to number of cores equals to 4. But if you don't have that one in real application, so if you submit a job, let's say later on to WestGrid, please make sure that this number matches with that job submission script. I'm sure that you already know how to write those job submission scripts. So the number of cores that you are requesting in the job submission script should match with the number of threads that you are using in your code. So it's a good practice to have this OMP num threads with S to set the number of cores that you specify when you're submitting your job. So here is, let's go in a little bit details of this program to see how it runs and what does this OMP do for us, OpenMP. So the first piece of code is similar, or this regular C code. We have some includes. And here is the program start just one thread. There's no more than one thread when you are starting until you hit this first pragma. So the pragma make the compiler create or fork more than one thread. So at that point, you create OMP num threads thread. So if you specify 4, you will create 4 threads and so on. So at this point, you have 4 running threads running on different cores of your machine, and each one will run this line of code independently. Okay, so thread number 0 will run this, thread number 1 will run this, and so on and so forth. And this one is just a function. It's part of that OpenMP library that I talked about. It's a runtime library. You can get some information. There are so many functions that we will see maybe one or two of that, one or two of them in this webinar. But you can have a list of those in one of the links that I provided at the end of this slide. So this is a function which gives you the rank or the number of thread number. So it will give you either 0 or 1 or 2 or 3, not 4. So this is not number of threads. This is the rank of each thread. So as I said, it starts from 0 up to n-1. And once you are out of this program OMP parallel or OMP end, when you hit the end parallel section of a Fortran code, what it does, it joins all the threads. So if you imagine you created 4 threads, it joins to 1 thread, and then one single thread will run the remaining code sequentially. So at this point, it runs just the sequential code. So that was the simplest program that you could write with OpenMP, but fortunately or unfortunately, the real-world application, they are not as simple as that one that we saw. So the first thing that you need sometimes variables. And why do you need variables? Because sometimes you need to do some calculations in the parallel region, but you want to, let's say, print the output outside the parallel region. And in the simple example here on slide 20, what we do, we are trying to say to print number of threads. We want to see how many threads we are using in this code. So you can see that I have this pragma OMP parallel section here. And then after that, I'm just saying that, okay, we had OMP get num thread. This is another function which returns number of threads. So it can return 4, it can return 2, it can return 12, whatever that you specify with OMP num threads. Okay, so this is the code that we are going to run at this time. Again, this is located at the same folder. It's called OMP hello world _ variable. If you want, you can compile it, you can run it. And if you run it, you will see that no matter how many cores you specify or number of threads you specify, you say OMP num threads equals to 4, this will print 1. It seems that you are running only on 1 thread. So, but don't worry, the result is correct, but the way that we are doing to get the result is not correct, because what we are doing here, we are getting, or we are calling this function outside the parallel region. And outside the parallel region, remember that your code is running serially, sequentially, not multi-thread form. So what we need to do, we need to call this OMP get num thread within a parallel region, somehow get the value, and then print it outside the parallel region. Okay, so that's how we are going to improve our program. Then we need some variables to get the value within a parallel region. And then once you have that value, which in this case is a simple integer, so you will get one integer which shows number of threads, and then you will print it later on. So in the parallel region, if you want to use variables, there are some keywords that you have to use. So you start with pragma OMP parallel, and then you will see, okay, default none. I will explain it in the next slide, and then shared end thread. So end thread is a local variable I specified here. I declared it here as an integer, and I'm going to use end thread to get my number of threads here. So I will explain this program in the following slide. So this slide number 22 is the C code, and it's available as OMP hello world _ variable, as I said. And here on slide 23, you will see the Fortran version of the same code. It's located at .f9t. So if you want, you can again compile it, check it out for you, and then I'm just talking about the details of this program. So default none, it means that don't assume anything about the variables of the variables in the parallel region. It's good because it will save you some time of debugging, because sometimes you don't know the default value, if it is shared, if it is private, or what. So when you say it's default none, it means that don't assume anything about the variables that I'm going to use in the parallel region. Then once you have this default none, so you have to do selectively, you have to make some of the variables shared and some of the variables private. And shared means that all the threads will see the same variables. And then once it's modified by one thread, the other one will see the results. So sometimes you need this type of variable, and sometimes you need private, means that each thread will have its own copy of this thread. Oh, sorry, will have a local copy of this variable. So if thread number 0 assigns something to this variable, thread number 1, 2, 3 will not see this value. So each one will have its own local copy. So I will make this my thread locally here, because I don't want, if you look at this code, this my thread is the thread number of my thread number, so I don't want to be shared with other threads, so I want to be 0 for thread number 0 and so on and so forth. But end thread is something that I want to share with all the with all the threads. So if I want to assign this one, assign a variable to a shared assign a value to a shared variable, then you have to be careful, because this shared variable is accessed by all the threads. And remember, all the threads are running all the time concurrently, so it's not serial. So you will see some unexpected results that I'll show you in the next example, that you have to be careful when you're updating or assigning values to shared variables. So what I'm going to do here, I'm saying that if your thread number is 0, just update this variable. Otherwise, this variable will not get updated. So we don't care, but in this particular example, I don't care which thread runs this one, but I only need one thread to run, because I don't want, let's say, 4 threads updating this end thread at the same time. So that's why I put this if statement. So the thread number 0 will come here. It will check the condition. Because it's 0, it will go through and it will assign this, it will call this function, and it will update end thread. The next thread, which is thread number 1, will skip this if statement, thread number 2 will skip, and so on. So only one thread will run this statement. And then once I'm out of this parallel region, I have a variable which is properly updated, and it shows number of threads. And then you will see that there are number of threads, and if you run this code, as I said, it's called OMP hello world underscore variable. You will see that this time it's running correctly, and then it returns the number of threads equal to whatever you set with that environment variable. Yes?
There is a question in the chat that if thread 0 is always the first one that started execution, or they start in random order?
No, they start in random order. So it's not like that. It's the first one that it gets the rank of 0. The second one gets 1. But the order of execution, as I said, it doesn't matter. So you have to be, sometimes you have to be careful when you are just, you don't have to do, or you should not assume anything about the order of threads. That's something that you have to keep in mind. Depending on the data that you are running on, depending on the system, each time you can get different results. And in this example, we don't care which thread is running this code. As long as we have only one thread running this code to update this end thread, we are okay. As I said, this is a just simple example to get the number of threads. So instead of running this or having this if statement, OMP has a different directive. It's called pragma OMP single, which means that only one thread will go and execute the line following the single directive. So all 4 threads will reach here, this line, this blue line here, but only one thread will go through. And it doesn't matter, it's thread 0, 1, 2, 3, 4. It's only one thread will go through because we don't care which thread is going to run. And once one of the threads went and then tried this statement, the other threads will skip. The same effect as having if statement. So once the one thread is inside the single directive, nobody else will run through this code. And the results will be the same. Again, you will have this code under OMP hello world underscore. Oh, this should be variable single.c or .f90. So you will have variable and then single. So this variable is missing here. Just to make sure that you see what I'm doing here, I'll share my screen briefly. So I have my export 4, then gcc-f OpenMP OMP hello world underscore variable underscore single.c, in this case -o OMP hello world variable single. Oops. Oh, be careful about when you are using -o. If you say -o.c, you will lose your source code. So I was about to do that mistake. OMP hello world variable single. And you can see that this result is there were 4 threads. So this number 4 is coming from the code that's it's within a single directive. So only one thread is running this code, and then the other threads will just skip. And then, as I said, we don't care which thread updates this variable. Sometimes you care, so then you have to run different sort of code. No, we don't.
So I know we don't care which threads.
Oh.
We know which thread eventually.
With single?
Yeah.
Okay, there's a question here locally that is there any way that we know which thread ran this code of this piece of code to update this thread? And with single command, I don't think that you have any way to get that, because single command directive has only one. Unless you have, oh, okay. So unless you have, I don't know if you can have 2 statements in the single. If you can, then you can have 2 local variables. Let's say one is OMP get thread num. to get the thread number, and then you can print it outside. An important aspect of OpenMP, and it's how we can make loops in OMP or OpenMP parallel or multi-threaded. And you know that in most of the scientific codes, you have so many loops, but most of the time, one or two are the main loops that they are doing bulk of the computation. And if you can make those loops multi-threaded and you can run it on multiple cores, you should gain quite a nice speed up in your code. The other, just I have to clarify a few things that most of the for loops or do loops in Fortran can be multi-threaded, but there's some specific conditions for OpenMP. For example, each iteration of a loop should be independent of the previous or next iteration. So you cannot have, let's say, variable I depending, which is the current iteration of the loop, depending on I-1, which is the previous iteration. So there are some constraints on the loops that which one you can or which one you cannot do the multi-threading. And the other one is, let's say, you cannot exit from a for loop in OpenMP. So if you decided to exit, all the threads will exit as well. So these are some conditions. But as I said, most of the time, your loops should be well-behaved loops that you can easily multi-thread, and then you can run the same for loop on different threads on different data sets. So let's say you have a big array. I'll show you two examples that exactly how it works. And another side note that is, I was working with few researchers that they were using R program, as I said, that statistical package, if somebody is familiar with. That particular package has its own set of directives very similar to OpenMP to make the loops in parallel. So if you get the idea here in OpenMP and you happen to use R, you should be able to easily apply your whatever you learn, hopefully something here, you can apply in an R package as well. Okay, with that note, there are two particular directives for loop in C and in Fortran. For C, there are OMP4, because most of the times you use for loops in C programming language, and in Fortran you use do loops, and because that's why in C you call it pragma OMP4, and in Fortran you call it OMP do. And because it's in Fortran, you have to close it with OMP and do, which we don't need it in C. And if your parallel region has only one for loop, so you can combine for and parallel, and then you can have OMP parallel for. So instead of creating parallel region and then creating for directives, so you can combine that, and then you can use pragma OMP parallel for. We will see one example using OMP parallel for. So this is the first example, very simple example of how loops are working in OpenMP. So here I have an example in C, and you can have it in OMP_loop.c or OMP_loop.f90. And so I'm just using a parallel region here, which is in the black bold. And in the future programs as well, those pragma or directives will be in bold font. And those who are the new directives, I put it in blue bold. So those are blue are just something that we just learned. So this in this case is pragma OMP4. I'm just writing before for loop. So when you have a pragma OMP4, there shouldn't be any statement before between pragma OMP4 and for loop. So the for loop starts immediately after this directive, and that's, as I said, it's a regular for loop. We have this I defined here, but by default, for loop variables in OMP are private. So every thread will have a local copy of I. So if thread number 0 updates its own counter I, thread number 1 and 2 and 3 and 4, they won't see this update. So they have their own copy to avoid this multiple threads updating the same variable at the same time. So what OpenMP does for you, it takes this range of for loop. So if in this case for loop is running 16 times, And if you define four threads using OMP num threads variable, what you will get each thread will get 4 iterations. So this is the simplest case. And hopefully, if we can get another webinar for OpenMP with some advanced topics, we will talk about the scheduling, that you can change the behavior of for loop, because sometimes your for loop, the way that they work is that initially you don't do that much of work, but sometimes some iterations have a larger amount of work to do, so that there's an imbalance if you just divide statically. Let's say the first 4 iteration is thread number 1. Thread number 1 just will finish it quickly, but thread number 2 should just run so long, just very for a long time. So that's why we can manage those imbalance. As I said, this is we are not going to see it in this today's webinar, but that's something that it's already taken care of in OpenMP. So in the simplest case, we have 16 iterations, 4 threads. The simple math says that give 4 iterations per thread. And if you run this code, if you go to the same folder, compile this OMP_loop, .c or F90, and then you run S1 with OMP num threads equals to 4, you will see that thread number 3 gets I12, 13, 14, 15, for example. The order of this printout will be different depending on when you are running your code. So if you run now, you will get different order. But thread number 3 should get 12, 13, 14, 15, no matter when you run it. So you may see thread number 0 becomes before that, but this number 12, 13, 14, and 15 should be allocated to thread number 3. And thread number 0 picks up the first 4, and so on and so forth. So as I said, OMP4, OMP do, and Fortran try to break up the for loop equally between a number of threads. It will try its best, but if you say you have 25 iterations and you have 4 threads, then somebody has to get more and somebody gets less. So, but OpenMP will try its best to balance as best as it can. And again, as I said, there are some other conditions that we have to take into consideration if we have different types of for. And there's another construct. Again, we won't see it today. It's called OMP task. It's introduced in, I believe, in OpenMP 3.0. And now its current version is OpenMP 4.0. But OMP task is something that was defined or introduced in OpenMP 3.0. We won't see it here. There's a question here, it seems.
Yes, we had a question about whether it is a Fortran question. So OMP 4 is a shortcut for OMP parallel 4, right? So it would parallelize single next for statement, right?
Yes.
But in Fortran, it has a closing statement.
Right.
So can you have more than one loop in between OMP do and OMP end do? Will they parallelize both of them? The single OMP close in Fortran?
So you have one OMP parallel do, but you have 2.
So if you want to enclose more than one loop between OMP parallel do, between OMP do and OMP end do, can you do that? Will it parallelize all of them, or it will take only the first one?
I don't know.
We don't know either. So.
For C, I know that it just picks up the first 4. But for Fortran, we can try it. I'll try and let you know. Just hold on to that question. That's a good question. But as I said, I'm not an expert in Fortran by any stretch, but I'll try that one for you. Or if you want, you can try yourself to see if you can put more than one for loop inside that. But we will try and get back to you. Oh, it seems that somebody is answering. I think only the first loop is parallelized. Masao is saying, okay. Yeah, That's what I thought too. If you have more than one loop, it needs you have to put OMP parallel and then OMP do for each of the loops that you want. And another thing that I mentioned, that by default the counter or the variable for the loop is taking private. But if you have a nested for loop, the second variable, you don't know what it is. So you have to specify it as shared or private. So it only takes the first for loop after this OMP4, OMP do directive in OpenMP. So there are some details that you have to work it out when you're writing your own code. So the first example here is it's just the multiplying the vector by a scalar. It's a scalar. It's simple, and this is just for demonstration only, because if you want to use this kind of operations in your code, there are some optimized packages and libraries. It's shipped with Intel compiler, with other packages like BLAS, that you should use those instead of reinventing your own wheel. So it's just here. It's a nice example to show you how the for loop works and how we can parallelize it. And the serial version is in daxp.c and daxp.f90. So if you want to compile it, run it to see how fast it works, you can run that. However, there is let me see, it's daxp.c. So to compile those codes, you can see here. Let me see if I can. Okay, so I'll share my terminal for a moment to show you how you can compile those, because it needs another C code, that's a utility code. It's called tic-tac, which gives you the time. So this is my terminal here. So if I want, this is the serial version, so there is no OpenMP flag, so it's daxp.c, and there is another, it's called tic-tac, again, .c. If you are compiling Fortran, it will be daxp.f90 and tic-tac.f90, and then you daxp, and then you can run this daxp code here. So you can see that it ran the code and it's registered as about 0.2 seconds or 200 milliseconds. Okay, so if you want to compile these codes, you need to put this tic-tac.c along with your other code. I have it in the slide for the next example, but I wanted to let you know if you are trying to compile this code. It won't work if you miss that one. Okay, back to this code. You will see that this code is here. I don't know, it should be readable, but again, you have it on your local folder. It's called in daxp.c, and here it's a utility for this course. It's called tic-tac.h, which gives or measures the time, and then you can use with two functions. It's called the tick and talk. Tick just starts the timer, and talk stops the timer and prints it. So these are the two functions that you will be able to use it. That's why you have to use this tic-tac.c or tic-tac.f90 with your code. And this code has two parts, similar to, like, again, many of the real world applications. Some part you have an initialization phase, and then you have a computation. In this case, almost the computation and initialization takes the same time, because it has the same for loop running for 10 million double numbers. And it basically just gets some numbers, initialize these two vectors of x and y. And in the main computation for loop, you run for the same lengths, and then you are just multiplying a by x, and then adding to y, and then you storing in z. So this is a computation, and this is the initialization, and this is the main function, which allocates memory for that. It defines a as to be 5/3, and so on and so forth, and it uses tic-tac here. Now we want to make this code parallel, and you can see here it's a GCC daxp here, TikTok is located here, so you have to compile those together, and then output will be DAXP, and then you run it, and it's almost the same thing that we got. It's about 220 or 240 milliseconds. Now we are trying to make this one, convert this one to OpenMP version. So we want to inject OpenMP directive. Now it's time for you, if you want, you can open one of those template files, either omp_daxp-template.c or omp_daxp-template.f90, and then try to write this OMP for loop, OMP for or OMP do the directives. I also put a comment so you can easily find where you have to write it. So you have to just basically type this # pragma OMP for in the proper location. I'll give you a minute, so if you want, you can just edit that code. If you can't, that's no problem. We have a solution for that. We will run it. We will see the result. But so there are three parts that I commented out. The first one, you have to put this pragma OMP parallel with proper shared and private, if you have any private or shared variable. And then you have two OMP4s, just one before initialization for, one before computation. Same thing goes for Fortran. So if you have to put this OMP do and OMP just OMP parallel blocks, but don't forget to close it in Fortran because you need end part. Is a question? No, okay. So if you get those, you can just compile your code and set this OMP num threads to 2. We start with 2. We will see if increasing the number of threads will give us any performance speed up. Or you can start with even OpenMP equals to 1. Just it seems that you are running serially, but because we already have the serial version and we have this number, it's about 240 milliseconds. You can skip this number, OMP num threads equals to 1, and then you can directly go to number 2. If your code works, that's great. If you couldn't make it, there's the same version of code that I already put directives, and it's called this OMP DAXP .c and OMP DAXP .f90. Those are the codes which its directives are already injected, and I will be discussing it in this slide and the coming couple of other slides here. So as I said, we need OMP parallel because we have more than one for loop. In C, you have to have a parallel region, and within parallel region, you have this OMP4s. And remember that pragma OMP4 has to be within parallel region all the time. So you cannot have it outside the parallel region. And look at the shared variables. I want n to be shared. N is the length of this vector. I want vector x to be shared, y to be shared, z to be shared, a to be shared. So I don't have any private variable here. Why? Because based on this I variable, which is controlling the iteration of for loop, and I know that I is private. So the first, let's say I have 4 threads. And I have 10 million, the size of the vector is 10 million. So the first 2.5 million of the elements of the vector will be assigned to thread number 0. The second one will be assigned to thread number 1, and so on. And if you have only 2 threads, it will be half-half. So I shouldn't worry about the X and Y to make that private. So every thread can have X, but it can only work on its own portion. So if you compile this code, gcc-openmp, OMP DAXP, don't forget this TikTok, otherwise you'll get error because it will be missing some functions that we are using in OMP DAXP. And the result or output or executable is OMP_DAXP. And we start with thread number 2. You run it, you will see that your runtime is 0.14, which is about 140 40 or 150 milliseconds versus 240 or 220 milliseconds. And as compared to the serial version, we have 1.65, so 65% speed, less time, or you are getting the 1.65 speed ups. And efficiency means that if you divide, you are using 2 threads, but you are not getting 2 times speed up. So 1.65 divided by 2, it gives you 83% efficiency. So in ideal case, you want 100% efficiency because you want to increase the number of threads and you want to get the same amount of work done. You want your work done as quickly as you get the number of cores increase. So if you get your cores from 2 to 4, you want your time to be half. So if you increase the number of threads to 4, so you don't have to compile or anything your code, you just need to write export OMP num threads to 4 to use 4 threads, run it, you will see that you are getting 2.81 or close to that, depending on, and you are getting less efficiency. And the third one, you cannot run it because, as I said, you are limited to only 4 cores for this webinar. But in a real-world scenario, if you have 8 cores, you could have run this one, but you can only get 58% efficiency because you increase your number of core threads to 8, but your speed up is only 4.67. So that's the reality that there are some overhead. So there is no free lunch. So if you want to get some speed up, somebody has to do something extra work, and OpenMP is doing for you by simplifying things, but threads needs to be synchronized and so on and so forth. So that's the price that you have to pay, especially when the number of threads are increasing. Okay, so that's one simple example that showed you how you can create your own parallel for, put proper directives, and you can get some relatively good speed up, especially if when you're moving from 1 thread to 2 or from 1 thread to 4. So you can get, it's pretty good speed up with good efficiency. So the other example that we are going to talk about is dot product of 2 vectors. This one will reveal another feature of OpenMP that you will need most of the time, and that we haven't talked about. So you will see that one. It's a type of variable that we will use for this calculation. Again, the serial code, if you want to run it for yourself for the first time to see how it works, it's called n.c and n.f90. So it's just 2 serial version of dot product of 2 vectors. Again, the vectors are the same size of 10 million double. So, and the code is here. It's a C version here. It's not Fortran, but Fortran code is in the same folder. Again, this symbol includes, and we have this n.dot function, which does the computation. This time we are not going to, because you already know how to parallelize initialization part or simple for loops. So we are focusing on the computation part, which is a little bit tricky because you need, as I said, extra feature from OpenMP. Otherwise, you have to write your own code, or you will see that you will end up with either slower code or incorrect code if you don't follow those guidelines. So the initialization is simple. We won't do it anything for computation. We are going to parallelize the computation part. So first thing first, we try this serial code. We compile it. There's no F OpenMP because these are the serial code, and then the output or executable is n dot. You run it. You see that this is the version coming from function versus that we calculate. It's here. Here we calculate, and in here it's analytically. So to make sure that the result of function is the same as the result of this calculation that we are doing. And this one is just showing that we have this 10 million doubles. And it says it's pretty fast. It runs in about 40 milliseconds or 0.04 seconds. Now we are trying to make it parallel. So again, I'll give you a minute or two so you can start trying to make it parallel with what we have seen so far. So you make it either parallel for. In this case, you can use parallel for because it's only one for loop in the parallel region. And the file that you want to get started, it's called omp_n._race-template. So this is the first attempt of doing it parallel. Again, I put some comments so you know exactly which line of code you have to change it. And I believe I put some, yeah, you have to just put one line for pragma OMP parallel for. And then you have to say which variable is shared, which variable is private. And you have just one variable, it's called tot or total. And then you have some variables like n, which is a number of elements in the vector or size of the vector. And we have two vectors of x and y. So you can just simply maybe copy and paste even from previous slides and so on. But don't go to the next slide because the solution is in the next slide. So I'll give you a minute. If you can, you just, as I said, put there, compile it, set maybe a number of threads to 4, and run it, and you will get a little bit of surprise because you will see that if you put everything in proper place, you will get wrong results, and it will be slower. Okay, so if you try this one, the first attempt should be like, okay, I have this total variable here, I here. I'll make the shared variable tot because I want every thread to contribute this tot variable because I want this tot variable or total variable to be the great sum of this dot product. So I want to multiply each vector element, and then I want to sum them up. So I want this tot to be shared among all the threads because I want this total to be the dot product of the full vector, not each piece that it's thread it's getting. So that's why I make it tot as a shared variable. N is shared, X is shared, and Y is shared. And you can compile it, gcc-f OpenMP, and this race, and with TikTok. And then you make it as ompn.race as executable, set the variables for, and you run it. You will see that you are getting wrong results. So you will just get 2.27 to the power of 20 versus 3.3. And the register is 1.31, which is 130 milliseconds versus 45 milliseconds that we had it before. So the answer is wrong, and it's slower. Now we want to go in details of what's happening. What's happening, it's called the race condition, which is a normal behavior when you have more than one thread on one process is working on the shared variable. So depending on which variable takes, which thread reads to which that variable first update, maybe the other threads won't see that result yet. So the first thing happens here, if you go to see in this table on the left side, you will see that the thread number 0 reads the total variable, which is initialized at 0. It puts in the CPU's register to do the update. While it's doing the update, it's called context switching. So it change the context from thread 0 to thread 1. Now thread 1 reads the total variable, but total variable hasn't updated yet. It still has the 0 value, so it will read the same 0 value to the register, to the CPU register, to have a local copy to make the update. Then thread 0 will update it, write it, so it will become 1. The same thing, thread 1 will get it, will update it, and because it has read 0, it will update it to 1, and it will write 1 back again to the total. But you are just missing one update, because here after 2 addition, you have to get total equals to 2, and in this case, we are missing 1. So that's the general idea or simplified description of race condition, that if you have more than one thread, as I said, you don't know the order of operations, and depending on the situations, you may get different results. And the bad thing about this race condition is that sometimes your code could work. Sometimes you can get the correct results, and sometimes you get wrong results. And that makes the debugging harder. So you have to make sure that when you have more than one thread, you have a proper synchronization in place and avoid this race condition as much as you can. So to avoid this or to fix this issue, OpenMP provides some directive. It's called a critical. It means that it creates there's a term in computer science that's called a critical section, which means that it's a section that only one thread or one process can run it. So it creates a boundary, or it's a fence around those variables or those statements, and only one variable, one thread at a time can run this code. So this is different than single. If you put it a single here, only one thread will update totes. That's not what you want. You want all the threads update this total variable, but in sequence, not at the same time. So that's why we need OMP critical. And if you put OMP single, you will, of course, you will get wrong results because only one thread will update it. But it will be maybe faster because the other threads will just skip that statement. So critical will guarantee that your code will work because it will be similar to your serial code. Every thread will come here. If 4 thread comes over here, 3 threads will wait. The first thread will go, update the tote, exit the critical section. The next thread, third, 4, and so on. And you can see that the overhead of synchronization is super high. So if you try this one here, if you compile this code, which is called n.critical, of course there's a template, but I think it's not much time left, so we can skip maybe updating the template by yourself because it's just simple line of code. You can compile it while I'm talking here, and then if you set the number of threads to 4, you can run it. You can see that you are getting the correct result. That is good, because if your program doesn't generate a correct output, it doesn't matter how fast you can run your program, it's useless. So the first thing is a correct result, which is good. The second thing is that you can see our speed is 50 times slower. Okay, so that's how much overhead is for synchronizing thread. As I said, it seems that 4 people are trying to enter from the same door. So every time 3 people will have to wait. The first one will enter, then second one will enter, the third one will enter, the fourth one. And this happens for 10 million times, not once, not twice. So that's why you have to pay so much price, and it takes 50 times more time to run. But critical section is very general. So most of the time, you don't need critical section. What you need something that's called atomic. Atomic means that, again, the load, add, and store all are one statement. So if I go back to this slide, I have here load, update, and assignment in 3 different machine states, machine steps. These are not programming steps. But in atomic, it combines these these 3 steps, and it will be run as atomic operation as CPU. So it will fetch it, it will update it, it will write it back before anybody else can read this operation. So this is a lower overhead, but there is not as general as critical section. It only applies for one statement following the atomic directive. And you can see that here, you can write it here. Again, the same thing happens that when thread 1 reads total, everybody else will not access this total variable until it writes back to its the value. So it will update total as one statement, it seems. So if you run this, you will see that its result is correct, which is good, and it's much better than critical section because, as I said, it's a much lower overhead. But still, it's 12 times slower than our serial version. So still, after doing these many things, we are not back to our serial version yet. Still, we are much slower. Again, this is cost of overhead, overhead of synchronizing threads. So how we can deal with fixing the overhead, fixing the slowness? What we can do, you can see here that, okay, we have only one tot, which is taking care of a total sum of vector. What if we have 4 different totals? Because we have 4 threads, each thread computes its own part of its vector. So it's, let's say, if it's 10 million, each one takes 2.5 million elements of the vector. Does dot product of that smaller piece, stores it in local total, and at the end we have only 4 statements to combine these local tots or local totals. So if you want, you can open that file, which is called OMP in._local-template. So what you need to do, you have to declare one local variable, which is going to be private, because each thread will have its own copy. And then you will have one statement at the end using atomic to add these local totals to the large total or the global total. OMP in.local-template. If you open it, you will see that I have 2 lines of comments. I already have OMP parallel for you and OMP4. So what you have to do, you have to define a local variable before OMP4 if you are using C, or if you are using Fortran, you have to put it before OMP. Or it should be, because in Fortran you cannot declare variables locally. You have to declare it in the outside the parallel region and make it private in the OMP parallel directive. And then you have to have one atomic directive to add those my totals or local totals to the global total.
There's a question in the chat.
Okay, so the critical is, as Gregory mentioned, critical is more generalized. So if you have more than one statement, and you want each thread does it separately, so one thread at a time, you need to create a critical section. But if you have only one statement, which in this case is only one statement or update statement, you can write this atomic here, and atomic will take care of it. As I said, this atomic is the subset of a critical, and it's because normally it maps to CPU's instruction set, which supports this atomic. It's much faster. But as I said, if you have more than one statement and you want to put it in a fence of critical, you have to use this critical section. That's good. Okay, so if there's no other question, I'll move to the next slide, which is slide 48. And we are trying to fix, as I said, fix the slowness. How we fix it? We say that instead of having one global variable, we can have 4 private, which each thread can update it without worrying about stepping on the toes of other threads. So each one will have its own local copy of, it's called the mytot here. And because variable defined inside the parallel region, it's private. I is private because it's a counter for 4. So this 4 will be divided by 4 because I have 4 threads. This 10 million, as I said, it will be divided in 4. So each one will get 2.5 million share. And then I have atomic. So this atomic will run only 4 times because I only have 4 my total. So that's why you have much less overhead. And now we are talking about speed up. So you will get 2.85 speed up by getting from 1 thread to 4 threads. And the good news is our answer is correct too. So you are getting the correct answer, and it's getting faster. So that's good. Not clear on Hussein's explanation of why critical is more appropriate. Okay, so if you imagine that instead of having just one, let's say in this slide, we have one statement calling total plus equals to. Imagine this is a few statements like this. You have a total, and then you have another variable doing another statement or another thing. Either you have a statement, either you have to have multiple atomic before each statement, or you can create one critical section, do some operation here. Let's say you do some if conditions or do something if you want to check. Let's say if you want to have an if condition on a shared variable and you want to do one thread at a time, you have to put it in critical section. So atomic, as I said, is just only for operations like plus plus or plus equals or plus one or some basic operations for updating variables. If you want to do anything fancier than that, you have to do, as I said, the good example is if you want to put if statement, and if you want that if statement to be run, depending on application, you may want to run that if statement one thread at a time, so you have to put it in critical section. So if it's not clear, again, so we will come up with another examples, hopefully, and then hopefully it will be clear enough for you. So we've got 2.85 speed up and correct answer by using local variables. So the basic idea is reducing overhead of synchronization is the one that you have to keep in your mind when you are working with OpenMP. So in this case, we have local sum and only P, or 4 times in our case, additions using atomic versus 10 million atomic operations that we had in the previous example. Since this operation is very common in most of the applications, OpenMP has a special directive. It's called the reduction. And the same way that you can say that, okay, my variable is shared or my variable is private, you can say that my variable is reduction variable. And for reduction, you can specify some operation. You can specify multiplication, like star. You can specify plus for summing, that's adding a variable, for adding the different values to this variable. You can specify, I believe, logical and logical or in C. And in Fortran, I think you can specify minimum and maximum as well. And I believe in OpenMP, newer version of OpenMP, you can have, I believe in OpenMP 4.0, you can have user-defined functions for reduction. So you can say that, okay, this variable is of type reduction, and here's the function that will do the reduction for you. So for complex cases, you can go for that. And reduction, what it does, it will do the same thing that you did manually here. It will create local variables for each thread, and at the end, it will sum or will add up depending on the reduction operation. It will add them up in this case, and it will store it back in the global variable that you have defined. So the speed up will be the same as you had it before, so you can't get better than that, but code is much cleaner and much easier. So you have one parallel for here. Of course, this int should be before that because this will complain. And your code is, and the folder is correct, but here this int has to move up. And here we have only 4 statements here and nothing before or after. So everything is taken care of by having this reduction here. And as I said, most of the heavy lifting will be done by OpenMP. So it will create local variable, add these local variables, put the proper atomic to make sure that your result is the same as you expected in the serial version. And your speed up is the same as that. Okay, so hopefully you could run this last example as well, which is called OMP reduction, which is the same as that one. And you can see for yourself that you are getting relatively good speed up, and then you get the correct result. Here we are done with the examples. There are some notes on the code that you saw, and then the conclusion will finish the presentation, and then I think we will have some few minutes for any other questions. So for this particular example that you saw for dot product, if you happen to have 8 cores, and if you increase from 4 to 8, you will see that there is no noticeable improvement in the speed up. If you do it, you will see it, and that gives you some indication that some of the programs, they are not. Sometimes you are not limited by the CPU power. It's part of the nature of the problem that you are working with. Even though you have thousands of cores, you cannot get more than some specific speed up because you don't have enough data to feed the CPUs or keep them busy. So that's something that you have to keep in mind, that having more CPUs doesn't mean that your code will run faster. You have to utilize those CPUs, and CPUs are good workers that if you don't, not so good workers, so if you don't give them something to do, they will sit idle. So there's no magic here, so you have to keep them busy. And this is just a simple calculation that, okay, so we have 10 million double vectors, we have 2 of them, and then each double is about 8 bytes, and if you multiply this by the number of seconds that we got from the speed up, you are limited to the bandwidth of memory on this particular machine that you are running. Normally on Grex, for example, your memory bandwidth, memory bandwidth means that the speed that you can move data from physical memory or RAM to CPU is about 9 gigabytes, or let's say 10 gigabytes, or in that neighborhood plus minus 2, that you can feed the CPU. So if you need more speed up, you have to have either bigger problems or do something else just to make sure that the CPUs have enough work to do. So if you just make it 8 cores, they will have less work to do if you have just only 10 million vectors. In conclusions, so we started with a brief introduction. Why do we need HPC, and why HPC, and so on. And one reason was just the new computers come with more cores, and even nowadays, if you are familiar with GPU or this graphical units, that they have maybe 1,000 core, or new Intel's co-processors like 5 processor that they have 80 plus cores. So there are more and more cores, but each core will be simpler. So as I said, if you run your code with the next generation multi-core CPU, you may get the same speed or maybe less, depending on what type of CPU you are using. So the good thing is that you have to take advantage of more than one core, and that's an opportunity for legacy codes to be optimized for new environment, and OpenMP is an easy and quick way to do it, because you saw that with injecting few directives. As I said, there are some details that you have to iron them out, but most of the cases it's as simple as putting those directives, and you can easily get up to, let's say, 12 times speed up on Grex if you get the full node, which has 12 running physical cores. So you can get the full node, and then you run your code, and hopefully you can get about maybe 10 times faster than your serial version. But this is something that getting good speed up is always a challenge. And if you need really scalability, you need to work on MPI, which is another library for writing codes to run on distributed memories. Remember that everything that I talked about in this webinar is about shared memory machines, that you have one memory and all the cores are using the same memory. So you are not going out of the one compute node. And the other good news is WestGrid has Tier 2 and Tier 2 supports. Gregory, for example, myself, or Masoud, that we are here, we are always happy to help you if you have any problems that you want to make it parallel, or you have a parallel program that doesn't run as good as you think it should run. We can just sit down, or we can help you. If you are local, it's in Manitoba, you can sit down here, or it's in Alberta. Everybody is willing to help you. If nothing happens, just you can send an email to support@WestGrid, and we will be happy to help you with any type of questions that you have regarding this WestGrid and your program and how to get best out of this facility that Compute Canada provides for all the researchers across the country. So here is some useful links. That first one is for openmp.org. It's the main website that it shows the latest news and developments for that. As I said, we have this programming section of WestGrid, which talks about this OpenMP and so on. We have different seminars, archive of seminars. The one that I posted here is something that's if you don't know which system in WestGrid, you have to use it because there are so many machines. Let's say Grex here, as I said, Hungaby and Alberta, Jasper, so on and so forth. If you are not sure which one to use, it's a good place to start. This is a seminar. It's a 1-hour presentation that it talks about the different features of each system. And again, if you are not too sure after reading that, send us an email and we will be happy, based on your application, we will be happy to help you to find the proper system to run your code on. And here is another, this is the last one, is a cheat sheet for OpenMP for Fortran. So it's a one-page document showing all the features of OpenMP. And the second last one is another webinar type. It's from Cornell University. It has some nice features and some nice examples that you want to use it if you like. So with that note, I am done with my presentation. So if you have any questions, I'll be happy to answer if I can.
There was one question that came in from Alina. I don't quite understand it.
For the question section with her? What are difference between what? For the question section. Alina, could you? Can we unmute her or him to see if she can explain the? Oh, between OpenMP. Oh, okay. Sorry. So MPI, or message passing interface, is something for distributed memory, and OpenMP is for shared memory. So OpenMP, as you saw in this webinar, it's very simple. It has some directives, but with MPI, you have some libraries, so you have to have some function calls. And then, if I understand your question correctly, that this is the question that you are going to ask, is the difference between MPI and OpenMP. So in MPI, you have to write your own function to divide this. Let's say you have a data set. Let's say you have this vector of size 10 million. You have to divide your vector, and you have to send it to different processes, because in MPI, not all the processes on your machine. So you have to say, okay, I'm sending the first piece to process number 1, the second piece to process number 2, and process number 1 will calculate will do the calculations, find the result, and send it back to 1. And in the MPI's model, we have a master process which does these communications, and it coordinates all these back and forth, getting and sending the data messages to different slaves, you call it. And then the slaves will do the job and then return the result back to the master, and master maybe will combine it and do the same, let's say, iterations and do something else, and then it will redistribute or finish the job. So that's how it's. But in OpenMP, all these details, most of these details are handled by library, but you are limited to only one compute node. So you cannot basically, let's say in Grex, you cannot go beyond 12 threads. So if you need something beyond 12 threads, you have to go to MPI version. Any other questions? There's one local questions here.
So what are the typical situations that we can use OpenMP? Basically, I saw from there are for loop and the while loop, and other situations that we can use.
Okay. So the question is, what are the situations that we can use OpenMP So we saw some for loops and so on.
Yeah.
Most of the time, loops are the best options for you. But as I said, that you have to just make sure that your loop follows the same guidelines. That doesn't depend. But as I mentioned, from OpenMP 3, I believe you can create tasks. Task means that some part of code or sections of the code, you can have multiple sections of the code, and those codes can run concurrently, even though they are not part of a for loop, but they can run concurrently on different threads. So depending on what you want to do in one program, you can create those sections and tasks and so on, and then do similar things that you could do with MPI within one computer. But as I said, the simplest case is just doing the loops.
Another question in the chat.
Are there a special trick to parallel read from a single file? Oh, I/O, it's hard to make it parallel, and in if you're asking the question that if multiple threads can read from different parts of the file, no, you cannot. But if the file is small enough, or the portion of file is small, you can read it from a file to, let's say, to memory, like a big matrix or vector, and then split that among the threads. But when you are doing I/O, you are just limited to the bottleneck, which is in this case is a hard drive or the file system. For example, Lustre file system, that's most of the global Scratch on all the WestGrid nodes are based on, has a parallel feature, so you will get a good good performance working with those, but Lustre is not good with smaller files. So if you have a small files, it's not good, but if you have a huge file to want to read and write, it's good. It gives you some performance edge using Lustre, but again, if it's not such a thing to run or open a file by multiple threads. So you have to just open once, read it, and then divide it among threads. So you have to remove or minimize the number of I/Os, especially even if this reading and writing, as I said, you have to minimize to maybe some special portion of your code that's the bulk of the computation that you are doing. Don't read or write from file while you are doing the computation. Otherwise, your speed up or the performance of your code will be limited to as a minimum as how fast you can read from that file. Okay, it seems that there's no other question. And if there's no more questions, we just end the webinar.